There's one where all you have to do is plug in the K you know, the temperature for that K, and then the other temperature. So this is the most direct way. And you get 0.0443 minutes. So here I put 127 and 50, right?
No.
You guys are all so smart in class. Somebody's going to do that on set. No. Dispel all temperatures that are not in absolute units. You don't even know they exist. Piece of trivia. Anybody know the absolute unit in the imperial scale? Yep. All right. Just curious. Everybody knew that one. Right. But chemical engineering you got. Imperial units, no problem. What else did I need? What else is in my equation? Speak up.
Epsilon?
Epsilon. What's that equal to? 2? No. Do not forget that epsilon also depends on the mole fraction of A in the inlet. In this case, it is 2. So those of you who all yelled out 2 and then I said no, you were right. But I don't want you to forget this, okay? So I made a point of making you feel bad for 2 seconds. So yeah, in this case, it's... And that's really because delta is equal to 2 and we have a pure feed. You're not going to have a pure feed that often. All right, that's really generous. So the volume, when all is said and done, 8.21 decimeters per minute, I believe, yes. Yeah, I didn't give you the conversion either. We're looking for the volume to give me 90% conversion. Okay? Say that I forget that. Is the volume going to be larger or smaller? If I solve the same equation, but I forgot that epsilon was equal to 2. I forgot that volumetric flow rates change. I solve this like a constant volume problem. Is the volume that I get going to be larger or smaller? Smaller, right? What did we just talk about, right? We just said that if I increase epsilon, then I get less reaction within my reactor. So by the same token, if I decrease epsilon by going from 2 to 0, that means I need less reactor to still get 90% conversion. So the volume that you would get if you had forgotten, and you can see it from the math, right? If this is 0, obviously this number is going to be smaller. You get 427 decimeters cubed. So, what's the actual conversion going to be if I had a reactor? You know, I screwed up, I built my reactor, I wanted 90% conversion, but I built it 427 decimeters cubed instead of 947. My conversion, so that's about half, right? My conversion will be about half? No, why? Because there's a log in it. That's a very pragmatic way to answer it. Because this is a first order reaction. And so as I do the reaction, right, the amount of reaction goes down. The rate goes down the further up the conversion goes. So you need more and more reactor to keep pushing the conversion up and up and up. So the conversion that you actually get is not half, but 0.71. that make sense? Right. The first inch of a PFR, I get X amount of conversion. The second inch, I get less. The third inch, I get less. And it'll just keep getting me less and less and less conversion as I go down. Yeah.
Is that 0.71? That's just the conversion of A. Does that have anything to do with the purity of the products?
No. If you were asked for the purity of the products, you would use the conversion and go back to your stoichiometric table, and you have that third column that says remaining, and everything was in terms of conversion. You plug it in, and then you just solve a mole balance like you would have 4 years ago, or 3 years ago. All right, any questions on this topic, and then we're going to start another one. Okay. Now we're going to talk about how do we deal with phase change within reactors. Every time I come into this room, I've lost a paper clip. It's not happening today. Alright, so we have a reaction. A in the gas plus 2B, also in the gas, reacts to form C in the gas plus D, which is both in the gas and in liquid. And we're going to do this in a PFR and at constant temperature and pressure. So first, why do I have a mixture of D? Some in the gas and some in the liquid.
Because it's going to be majority, if you want to produce the liquid as vapor pressure.
You're going to produce a gas. You're going to produce too much of it, right? And I think that's what everybody's saying. You're going to exceed the saturation pressure, or you're going to exceed the vapor pressure, and at that point, you're going to condense. But this doesn't mean that we're producing the liquid directly. We're still producing a gas. So are we always going to make liquid? No. We have to be at a certain conversion, and we're going to talk about that in more detail. But yeah, you have to be at a certain conversion where you've made enough D such that the pressure of D is greater than the vapor pressure of D, right? That's when you're going to get the condensation. So, DLE. And now we got to be a little bit careful because now we've got two different types of equilibrium. So we got to be careful in what language we use. I know some people said equilibrium when I asked the question. Is that a reaction equilibrium or vapor-liquid equilibrium, right? So just try to keep in mind that we have two different types of equilibrium. Don't let it throw you off. Okay, so this should haunt you as it does me. Where's the equation go? Fugacity equals fugacity, right? The mole fraction of D in the liquid, no, sorry, that's a little e. So we're going to say VLE, meaning at vapor-liquid equilibrium. The notes just say E, so if you see me just put E, yell at me, because I don't want you guys to be thinking about chemical equilibrium instead of phase equilibrium. So yeah, the mole fraction in the gas, that's why it's Y, of D VLE times the pressure. What's this? Fugacity coefficient? Mole fraction fraction now in the liquid, so we switch to X. The saturation pressure of D and gamma D. What's gamma? The activity coefficient. All right. Ah, thank you. V L E. Okay, so again, this only happens at certain conditions. So one of the first things we have to do is figure out which conditions those are. But we're going to simplify some things. How many species can condense? Both of them can. Everything can condense. How many species can condense in this problem, given the way that I wrote it? 1. But they can both condense in reality. It just means that we're not actually going to operate at conditions where the other one can get close to condensation. So what's the mole fraction of D in the liquid? Unity, right? It's a pure liquid. Since it's a pure liquid, what else do I know? Yeah, let's not say gamma, but the activity coefficient, also equal to 1. And what are we going to assume about the gas phase? Ideal. So what else is equal to 1?
You guys take over?
Yeah. Okay, so that goes away, that goes away, that goes away. That's helpful. And I get it. Anybody remember what that's called? Raoult's law. Yeah. All right, so it simplifies down to Raoult's law, which is nice. And remember, the pressure is given, right? Or it's going to be given. Don't worry, you guys. Okay, so if the pressure is given and the vapor pressure is given, I need vapor pressure as a function of temperature, but we know how to do that. And the pressure is going to be given. Okay, so if the pressure of D is less than the vapor pressure, then does D condense? No. So we only gaseous. And then what's true about the vapor here? Right. So the mole fraction of D, again, if I'm at that vapor pressure, then the mole fraction of D is equal to the mole fraction of D at vapor liquid equilibrium. And so as X increases, what happens here? Does this change? No, not if I've told you that you're at vapor liquid equilibrium, right? This isn't yet a mass transport course. So if you're assuming that as you keep making more and more gaseous D, it equilibrates with the liquid, then you know that all D ends up extra D, right? We just keep adding D, we get more and more D in liquid. It just keeps going up and up and up. But the mole fraction of D remains at its equilibrium value in the gas. So we keep doing the reaction, we get more and more D, or we should have gotten more and more D, but we can't actually get above this amount. Yeah.
But at that condition, X is always equal.
Which is, no, the conversion?
No. Oh.
Yeah, sorry, this is conversion.
Oh, that's conversion. Oh,
Yeah.
okay.
This is the X, the big X.
Thought that was the fraction. Of the
Yeah, sorry. Big X conversion. And so here, as the conversion increases, right, we keep increasing the partial pressure of D. So you're increasing the partial pressure of D until you get to equilibrium, at which point you can no longer increase the partial pressure of D, because all the extra D you put into the system now goes into the liquid phase. So that means our stoichiometry table just got nasty. We've got to write out two of them. Because there's two different regimes in which we can operate. We can operate in the regime where we only make gaseous D, or we could operate in the regime where we're making liquid D. So, I didn't tell you, but now I'm telling you, feed is stoichiometric. What does that mean? What piece of information did you just gain?
Want to get into the coefficients of the equation?
Yeah, so if I want to put it in math terms, FB naught is equal to what?
2/3 FT naught.
2/3 FT naught's correct, but you're just a step ahead. Alright, the species A, B, C, D. No C, no D. Again, because I told you that the feed was stoichiometric. That also means no product. The change that we get minus FA naught X minus 2 times FA naught X FA naught X and again FA naught X. So this is the other thing that might throw you off. Up until now, we haven't had to worry about whether the flows that we're writing down were moles of liquid or moles of gas, because we didn't have any phase change. So if we were dealing with a liquid system, they were liquid, like a CSTR. If we were dealing with a gas system, they were gas, like a TFR. Now we actually have to write them separately. Okay? So I'm going to write out what's remaining in the gas phase when the partial pressure of D is less than the vapor pressure, and when the partial pressure of D is equal to the vapor pressure. Remember, we can't go above the vapor pressure because we're at equilibrium. And now the flows that I'm writing down are just gas phase flows. So when we write D, we're going to need to write two flows. Okay. This is FA naught times 1 minus X, like it was before. Two minus 2X. This one has not changed at all. Because I'm not at a condition where I condense D. So, when you're at this condition, forget the phase change part, right? It doesn't matter. This is the same that we would have gotten when we first did stoichiometry tables. This one's a little bit different. No different for A, because A cannot condense. Same with B. Same with C. What's D? Remember that when this is true, I know what the mole fraction of D is. Right? FD is equal to the mole fraction of D at equilibrium times the total flow. And now you can add all that up, and the total flow I'll rewrite them over here. So you can think of it like a trick. If I'm at a condition where I'm condensing D, then I get the mole fraction of D not from thinking about this class, but simply from vapor-liquid equilibrium. I get the mole fraction of D. So if I know the mole fraction of D, all I have to do is multiply it by the total flow rate, and I get the molar flow rate of D. And how do I get the equilibrium mole fraction of D?
Is that supposed to say FT not on the right side of the equation?
Yeah, I'm going to write it again right here. So this is, I've done algebra to it, but that's all. Right, because you see the FT is on both sides of the equation. Because it's inside the expression for FD, so that's why it's on both sides. So if I rearrange and solve for FT, that's what you get. Alright, things just got tricky, huh? Get a lot of blank spaces. How do I get this? We already had it on the board, right? You guys named it. Ralph's law. So I haven't changed that much. All it means is that for the species that can condense, when I'm under a situation where I am condensing it, I just get the mole fraction from Ralph's law. That's all. The bigger question is, when does this occur, right? This obviously occurs as a function of conversion. The more I react, the more D I make. So that's what we're going to do next, is figure out at what conversion this will occur. So if I plot the total flow rate versus the conversion, is it a continuous function? Under normal circumstances, but not this time, because I have two different flows, two different equations for my flow rate. And again, even though I'm writing this in terms of pressure, this is really a question of conversion. At what conversion am I at? Because the higher the conversion, the higher the pressure of D, since it's a product. Yeah.
Before it has to be a continuous function of X, because you can't.
Maybe I used the wrong word. It's not, there's a kink.
Yeah, but it has to be continuous.
Yeah, so what's the word that I'm looking for? It's not differentiable, but yeah. Yeah, the notes say discontinuous, but I think you're right. That it's continuous. I understand what you're saying. Right. But I think what you're, otherwise you'd be doing things that aren't conserving mass, so we generally want to conserve mass. But yeah. The note, like I said, the notes say continuous, but I think we want to say that it's not differentiable. Yeah.
One thing that doesn't make sense to me is that when you look at the overall equation, you have A plus 2B goes to C and D. You would think that as the reaction progresses, the pressure would actually decrease because you're producing less moles.
The total pressure might decrease, but not the partial pressure.
Okay.
Because I'm making D. The partial pressure at the beginning is 0, so it has to go up.
D is dependent on its vapor pressure. It has a unique vapor pressure. So
Even if it didn't, the partial pressure of D is going to go up, whether it can condense or not.
Oh, I see what you're saying. Okay.
It actually stops going up once I hit the vapor pressure. It can no longer go up, but the partial pressures go up. You're thinking of the total pressure. Total pressure, but again, remember we're at constant pressure.
Right.
So it's not actually even that the total pressure
As long
changes.
as D, the partial pressure of D reaches its vapor pressure. That's
Yeah, I mean, that's what we have right here.
all right.
PD, this is partial pressure, yeah.
That FT is just for the gas phase, right?
Yes. Yeah, like I said, it gets tricky because now suddenly this has a different meaning. This is just the gas phase flow rate. And part of the reason why we leave it in terms of the gas phase flow rate is the amount of D that we're condensing does not affect the concentration of A. Right? A's in the gas, D's in the liquid. I put more liquid in. It's not going to change the concentration of A. Okay? Not if we're at constant pressure, which we are. So we want to keep all of our flow rates in terms of the gas phase because that's where my reaction is taking place. My rate law is based on gas phase concentration. All right, so let's look at an example. Really, let's continue this example is what I should have said. Now I'll start putting some numbers up. Pressure. Given some more stuff. Given that the vapor pressure of D is equal to 16 kilopascals at 300 Kelvin, you don't have to worry about changing the temperature. And given that the rate equation is that. Now what we want to do is find equations for rate and total flow rate in the gas of conversion. All right, so any questions about what you're given? Okay.
Let's look at K, right?
Only if I was at, not right now, because I'm just saying find rate as a function of conversion. So K can still be in there. But yeah, if I was asking for a volume of a PFR, you'd have to be given K. Okay, so let's start with what is the mole fraction of D at vapor-liquid equilibrium? What is that?
It's the part pressure divided by the total pressure.
No. Well, yeah.
It's the
But
PVD divided by P.
yeah, that's what we actually wanted. We want the vapor pressure divided by the total pressure. 16 kilopascals divided by 101.3 kilopascals, so you get 0.158. And YD is equal to the flow rate of D divided by the total flow rate, right? So let's take what we had earlier, which I erased when I actually put it just in terms of FT. We'll put it on the board and we get FA naught X over so that's just that first one, okay? And so when you're at vapor-liquid equilibrium, then YD is equal to so I'm going to use XC to indicate critical conversion, yeah.
Could you also solve where the two phases of FT equal to each other find the conversion and solve back to find YD? Because those have to be continuous.
Yeah, but the point at which they meet depends on YD. If you rearrange those equations, you're going to get.
But if you get y, you got yd already.
No, I'm using the definition of yd. Just to set this up. And then I'm going to say when yd is at equilibrium, then we'll actually solve this, but now, so the FA knots cancel, and we just get x over 3 minus x. But now it's not a generic x. This is only true at a specific point.
You have all the information for step before.
No, I know. I mean, I didn't say that I didn't. I'm just working through the problem, right? You don't need the number for, that's all I've done in this problem so far, is solve the number here. The number doesn't matter. This is true always. It's not just true when this is equal to 0.158. Okay, but we want this critical conversion. This critical conversion is when we start condensing D, right? So that's what we're solving for, and we're just using this equation of the definition of yd, and then setting that equal to, we can do it numerically now by setting it equal to Raoult's law. Yeah.
Just to be clear, is this yd before you started to condense?
This is either. It remains constant once you start to condense, right? It stays at the equilibrium amount. So I can use the form for the vapor to start, and then you end up here. But remember that it's a function that has a kink. So what we're trying to do is find the conversion corresponding to that kink. And it depends on the stoichiometry, but this is what you get for this problem. Okay, so if we do that numerically, we get the critical conversion is 0.41, 41%. So at higher conversions, we're going to be condensing D. At lower conversions, there's no condensed D. We don't have to worry about it at all.
And that's when the graph slope changes at that point?
That's also that kink.
I have a question. How
Yeah.
do you know yd is big? Did that give it to you?
That's Raoult's law.
Oh, Raoult's law, okay. So you know the flow pressure.
I know the vapor pressure and the total pressure, so I just use Raoult's law to get the molar fraction of D at vapor-liquid equilibrium. No, no. It depends on the stoichiometry of the reaction. It depends on the vapor pressure, the total pressure, everything. Yeah. Okay, so when the conversion is less than the critical conversion, then we solve it just like we have before, right? So again, we need to put concentrations in terms of conversions. When this is true, then it's pretty simple. It's just Ca Fa over the flow rate. Is this changing? Does volumetric flow rate change? Why not? Because you're guessing? You had a 50-50? Yeah, it's a gas phase reaction at constant pressure. So it's probably changing unless epsilon happens to equal 0. And we'll also write out that Cb, because remember now we need both. Because our rate equation has both concentrations. And I wrote out over there, this is Fa, this is Fb, so we use those. We need an expression for the volumetric flow rate, how it changes. And that's just the initial flow rate times 1 plus epsilon x. And again, y is because isothermal and constant pressure. So what's the initial mole fraction of A?
One-third.
1/3. Right, stoichiometric feed.